There are many forming processes that are used to take metals from a beginning shape to an end shape. For example, a metal sheet can be rolled from one thickness to a smaller thickness, or you can bend metals in various ways. There are many ways that a metal can be permanently shaped or plastically deformed. We talked about plastic deformation and the mechanism of plastic deformation in a previous video. So my question to you is, do you think that the metal before it is deformed and after it is deformed is the same? That is, does it have the same properties? The answer is no. The metal will have different properties in the region of plastic deformation. If the deformation happens at room temperature, for example, this is called cold working. So what is cold working? Well, no, it's not working in the cold. Cold working is plastically deforming a metal below its recrystallization temperature. What is that, you say? Okay, let me back up. We know what plastic deformation is, but what is a material's recrystallization temperature and what does that matter? I think it's best to describe what happens to a material if it's heated above its recrystallization temperature. Remember that all materials have defects. Above the recrystallization temperature, damaged and defective grains and crystals start to repair themselves and attempt to become perfect again. So if you plastically deform a material below its recrystallization temperature, you are creating more defects and not allowing the material to repair itself. The more defects you create, the harder it is for plastic deformation to occur, and hence you get a stronger and harder material. This is why they also call cold working, work hardening, or strain hardening. If you start with a ductile, not very strong material and cold work it, you can end with a strong, hard, not very ductile material afterwards. So how do we define cold work? And why would we want to define it? We usually define the amount of material has been cold worked by the percent that it has been deformed. For example, say you have a sheet of metal that originally has a cross-sectional area of 1 inch by 6 inches, and after you roll it, it has an area of 0.5 inch by 8 inch. How has the area changed? It went from an area of 6 inches squared to 4 inches squared. If we calculate the percent change in area, we can use the formula change in area over original area times 100%. That would be a 33% change in area. That is how we define cold work. Now on to the second question. Why do we want to know the percent cold work? Well, experiments have been performed on different material that correlate the percent cold work with the amount of strength increase. So if you want to produce a certain strength in a material, you can grab the appropriate graph and then you can determine how much you need to cold work that material to achieve that strength. Let's take a closer look at the graph that you see. This particular graph is for copper. Do you remember when we talked about yield strength? The yield strength is the stress that you have to apply to a material to get it to plastically deform. Anything below the yield stress, and you only get elastic deformation. Anything above, and you get plastic deformation. So you can see the more you cold work the copper, the higher the yield strength becomes. But what else do you see on the graph? There's a curve that is labeled percent elongation. What does that represent? Percent elongation is what is the extent to which you can change a material's length before it breaks. It is a measure of a material's ductility. So when a cold worked material gets stronger, what happens to its ductility? Right, it decreases. What else do you see on this graph? There is one more curve. Tensile strength. The tensile strength is the maximum stress that can be applied to a material before it breaks. It is also a measure of how strong a material is. All right, one more question about the graph before we leave it. Why do you think the graph ends at 80% cold work? Why doesn't it go to 100% cold work? Well, for copper at least, 80% is the maximum amount of cold work that can be done before the metal breaks. It can't be worked beyond that. Another material might have a different percentage that it can be cold worked. Remember, each material will have their own graph. So what happens if we want to roll a sheet of copper from 1 inch by 6 inches to 0.1 inch by 6 inch area? That's 90% cold work. It would break. Well, how do we manage that then? Well, we have to place an intermediate step in between and anneal the metal before we can cold work it again. Annealing gives back the metal's original properties and makes it soft and ductile again. Annealing reverses the effects of cold working. But what is annealing and how does it work? Annealing is simply taking the metal up to an elevated temperature and allowing it to heal itself. There are 3 stages to annealing: recovery, recrystallization, and grain growth. In the recovery stage, the temperatures are at the lowest range. Residual stresses start to recover, but the mechanical properties remain virtually unchanged except for conductivity. In the recrystallization stage, as the temperatures rise, the strength of the material will decrease and the ductility will increase. At the highest temperatures of annealing, grain growth will start to grow, or grains will start to grow. This stage is usually avoided, as this will have a negative impact on the material properties. You can cold work a material, which means you form it below its recrystallization temperature. But you can also hot work a material, which means that you form it above its recrystallization temperature. In general, cold working is done at temperatures less than 30% of a material's melting temperature, and hot working is done at temperatures above 30% of a material's melting temperature. So if cold working gives you a strong material, why would you want to hot work something? Well, hot working a metal allows you to get large deformations without multiple steps and annealing in between, like you may have to do with cold working. It also takes less energy to deform the piece because it's hot and less strong while you're forming it. Some disadvantages are dimensional control. When you heat a metal up, it expands, then contracts when it cools. You have to take that into account when you're designing the forming process. And heated metals oxide more rapidly. Do you see the oxide film in the picture in the upper right? This means that the surface finish is worse for hot worked pieces than it is for cold worked parts.